At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day, sir!
Hi, welcome to CheMistakes. Here I'm going to be going through a student response to a calorimetry question, try and give you an understanding of where the student went wrong and how to avoid that when you do the problem, so that way hopefully you can gain an understanding of what's going on here. So we have a question, we have a hot piece of metal, 100 degrees Celsius, we put it into cool water, 20 degrees Celsius, a little more water than metal. Gives us the specific heat capacity of the metal. Water specific heat capacity, of course, we just know. The question is, what will the final temperature be? Okay, so the student response, they set Q equal to Q. They plugged in mCΔT, or MCAT, as I like to call it, for the one Q, and mCΔT for the other Q. They then plugged in all of the metallic stuff over here. So 50 grams, 0.9 for the specific heat capacity, final temperature minus the initial temperature. Then all of the water information is plugged in here. 100 grams, 4.18 for specific heat, final temperature minus 20 degrees. The final temperature for this and this are the same. The point where the metal and the water reach the same temperature is the point where the temperature will stop changing for both. So they then multiplied this out to get this equation on the left, this equation on the right. They pulled the T-finals, temperature finals together. They pulled the amounts of this together, solved, and got 10.3. So a small problem with that is that we're looking at, initially we're dealing with a situation where we have some water. It's at 20 degrees. We take a big chunk of metal at 100 degrees, put the chunk of metal into here. We would expect the temperature, the final temperature, to be somewhere between 20 and 100. It doesn't necessarily need to be the average of the two at 60, but having a final temperature of 10.3 should indicate that something went wrong here in the calculations. Okay. So to help us organize our calculations a little bit, perhaps it would be good if we started with what are called LOL diagrams. So in an LOL diagram, what we do is we track what's going on with the energy within a system. So we're going to do one for the metal, and we're going to do a second one for the cool water. And we're not looking at the amounts yet, we're just trying to gauge what's going on. So if you've never seen an LOL diagram and you're curious to see a little more, I'm going to link a little video in the description, and you can see it running along the video right now. So if you want to click on that and then come back here. So for the thermal energy of the metal, the thermal energy starts off very high. I'm going to give it 4 bars of thermal energy. And the bars here are not quantitative, just to give us kind of a qualitative idea of what's going on. Phase energy, the metal is probably solid at this point. So it cools down to some final temperature. I don't know where that is. Well, let's just say for a second it goes to 3 bars. It's going to stay as a solid like this. So what's happening is the metal is losing energy, or energy is exiting away from the metal. So I'm going to draw an arrow leading away with one block of energy exiting the metal system. Now the water, on the other hand, starts out cool, so we're going to give it 2 bars of thermal energy, room temperature. 2 bars of phase, starts off at a liquid. And then at the end, it's still going to be in the liquid state, so our phase energy isn't changing, but our thermal energy is going to go up. So let's go ahead and just give it a 3rd bar here. So we're gaining a bar of water, or gaining a bar of energy for the water. So what we're seeing happening is the energy is moving from the metal into the water. So if we were to do that in terms of heat, the Q for the metal is going to be equivalent to the Q for the water, with one big difference. The direction is different. So the energy is leaving the metal, the energy is going into the water. So the last thing we need to do is we need to put a negative sign on one of these because the direction is different. So this is decreasing in energy, this is increasing in energy. And that's the critical difference between what happened with the student and what you should do for the correct answer. The only thing that really is messed up here is that they should have labeled this with one of these being a negative. And they probably should have put in that one is a metal and one is for the water. But really the negative sign there is the big difference between this being right and wrong. So if we were to redo this analysis now, we could go back through and we could say, okay, so the energy going into the metal is equal, or I'm sorry, the energy, let's do the energy leaving the metal, right? So the energy leaving the metal is equal to the energy going into the water. And now that we have Q's here, we know that we can plug in mCat for this, where every single feature of this is about the metal itself. So we want the mass of the metal, specific heat of the mass of the metal, and the temperature change of the metal. So we're going to do 50 grams of metal, and then we're going to have 0.9, and we're going to have the final temperature minus the initial temperature of the metal, which is 100. Now over here, we have the same thing, but towards the water. So we want the mass of the water, which is 100 grams, specific heat of the water, which is 4.18, times the temperature change of the water, which is going to be the final temperature minus the initial, which is 20. Now if you're paying attention here, the key here is that the T final minus 20, the final temperature is going to be somewhere between 20 and 100. So this value is going to be a positive value. This value is going to be a negative value because we're ending at a temperature below 100. So the negative signs are going to cancel here, but we need them to do that canceling because up here, this answer is not actually working out in a way that makes any sense. Okay? So what we're going to do now is we're just going to distribute everything. So we're going to do negative 50 times 0.9 times T final. So that's going to come out to negative 45 final temperature. And then the 45 times the 100 is going to be plus 4,500. And then over here, we should end up with the same thing as we ended up with over here, which is 418 final temperature minus 418 times 20, which is 8,360. So let's clear ourselves a little room here. We just need to do a little bit of algebraic manipulation here. We need to pull the final temperatures together on one side. So 418 plus the 45 is going to be 463 final temperature. And then the 4,500 and 8360 are going to add. So we're going to pull these over to the other side. So we're going to end up with 1,200, 860. So our final temperature should be the combination of those two. And at this point, I've run out of work, so I'm going to have to plug into the calculator briefly here. And that comes out to be 27.8 degrees Celsius. Now let's check our sig figs here. We start with 4 sig figs here. It's like 1. Let's add a little decimal place there so we have a more reasonable amount. So 3, 3, 3, and 3. So let's end with 3, so this should be good. And then let's start to reflect on, does this answer make sense? So I'm between 20 and 100. That's a good start. I'm closer to the water, which makes sense because the specific heat capacity of the water is larger and its amount is larger. So we have twice as much water in terms of mass as we do with the metal, and the specific heat capacity is over 4 times as much. So we would expect the metal to change by at least 8 times the amount. The metal went down by about 72 degrees. The water went up by a little over 7 degrees. So that looks like close to a 10-to-1 ratio, so 8 kind of works out. So this looks like a very reasonable response, and looks like we've gotten it right. Now, the key on that, though, going back to this, is that we're setting up that negative sign appropriately for both sets up the algebra correctly. Now, the last thing that we can emphasize on this drawing here is that the metal is losing energy, which means that this process is exothermic with regards to the metal, but it's also endothermic with regards to the water. And that's interesting because often in chemistry, we isolate these terms and we say, what's going on here? Is this exothermic or endothermic? And the reality is there's always one of both. If something is gaining energy, something else is losing energy. And so we often misconstrue or mix these up because we don't look at both the system and the surroundings. And if the system is losing energy, that's exothermic for the system, but that means the surroundings then is going to be the opposite. It's going to be endothermic. And so that's a really critical idea that can really help avoid a lot of mistakes like this that will eventually come into problems in calculations.
Okay, a simple wrong would have done just fine, but